Hi, this is Lecture 13, lucky number 13. And in this lecture, we're going to be talking about ripple-free deadbeat design. We're going to continue our discussion on this, and we're going to focus primarily on performance in this lecture. So we talked a little bit about performance last time, but just kind of giving some basic examples. We're going to look now at a general approach to solving this problem and how to develop tools to be able to handle the kinds of problems that we're going to be looking to solve. So in this particular case, we're going to be looking at solving the performance program. So we've talked about these other aspects of control design, and so the performance program is how we address the issue of performance. Here's our basic control structure that we've been using. So we're looking again at everything in the ideal case. So we have a plant that we assume that we know fairly well. We're going to design a 2 degree of freedom controller. So again, it's 2 degrees of freedom, has 2 inputs, 1 output. So you can think of it as having 2 controllers. Now the need is the issue of performance. So the minimum order solution satisfies all of the basic requirements: internal stability, deadbeat tracking, ripple-free settling. That's awesome. But it's often not quite enough. The minimum order solution also has the nice property that it gives minimum settling time for that particular sampling period. And so the question is, how could it get any better? Well, unfortunately, the minimum order solution also has drawbacks that can be significant. So, for example, consider this system, okay, unstable, definitely needs control. The minimum order solution can make this system settle in 0.4 seconds when the sampling time is 0.1 seconds, so in 4 steps, so which is pretty common for a system that has 4 poles. But if we look at the response of the system when a step input is applied, this is what the response looks like. Look at that overshoot, huge. And the control magnitude, 10 to the 4. Wow, 10 to the 4. That's like 30,000 volts if this were a motor system. That's a lot. Whoa. So, huge overshoot. Okay, so this is not a good response. This is the response we get from the basic design. Now, so this is for the sampling period t is equal to 0.1. We could actually see what happens if we change the sampling period. What happens, for example, to the overshoot. So for example, here is the same system, and now we've applied the minimum order solution for each of these sampling periods. Notice that when we do this, basically for each sampling period we get a new discrete time model, right, using the H transform, and then based on that model, which has the same number of poles, it'll have the same number of poles as the one at 0.1, and so these are the response we get. So notice that as the sampling period gets smaller, the overshoot gets large, and actually at 0.01 it's like 70, and then as we increase the sampling period, make it respond slower. So notice it takes almost 1 second for the system to settle here. It has significantly low overshoot, but still pretty large. So this is 1. This value it settles to is 1. So this is still pretty large overshoot, even when it takes 1 second for the system to settle. So these are some of the kinds of things that we have, and basically it shows that the performance definitely needs help. Definitely needs help. And in general, what we'll find is that there's a trade-off between speed of response, for example, settling time, and maximum control magnitude. In engineering, a lot of engineering problems, there are trade-offs. You know, if you want it to respond fast, for example, if you want it to settle quickly, that means you're going to have to give it a big push initially to get it moving, and so forth. And so that's the kind of thing that generally happens. Since a system often has control magnitude limits, the large magnitude is unacceptable. We can't We can't, we couldn't put that system into the lab and get it to work. We can't produce that kind of voltage. So the question is, how do we work with that trade-off? How can we give up some of the settling time, for example, in order to reduce the control magnitude or the overshoot, for example? So the overshoot we saw was really large, and if we allowed the sampling period to get longer, we could reduce the overshoot, but can we do better? That's the question. And so our problem boils down to this. We may have what's called a performance program that basically looks something like this. This is an optimization approach. And so we would say, I want to minimize the transient control energy. How much energy is required to undergo this step transition, this step maneuver? Okay, how much energy? Can I minimize that? And I want to do that subject to some conditions. I want the overshoot to be less than 5%. I want settling time to be less than 0.3 seconds. And I want the control magnitude to be less than 10. Okay, so these are the kinds of constraints one might impose on a problem. In other words, I can't allow huge overshoots. I can't allow long settling times, and I can't allow large control magnitudes. I have limits. And so we impose those limits in this problem. And so now the question is, how would we solve a problem like this? Okay, this is the kind of problem we're looking to solve when we look at performance, analyzing the performance of a system. So now, what's so important about the control signal? For example, the transient control energy is one thing we were minimizing. What's so important about the control signal? Well, in generally, it supplies the energy the system needs to do whatever it's going to do. It needs to be both precise and strong enough to make the system do what it needs to do. There are often limits, magnitude limits, energy limits. So, for example, the energy limits could arise, for example, if this system that we're trying to control is, let's say, it's a satellite, and we're trying to work with the attitude control. That is, we're trying to position this thing so it's, for example, suppose it's the Hubble Space Telescope. We're pointing at this place. We want it to move over and point over here. Well, it has a limited amount of energy available, and so you don't have an infinite amount of energy to move from here to here. You have to guard your energy, and so those are important things that can arise in a problem. And so generally, minimizing the control energy often will result in a good output response. So that's good. All right, so suppose we have a performance program. How do we find the control sequence that solves that control program? And in particular, can we describe the control sequence as a function of the unknown? Remember, V1 was the unknown or a free parameter in our Diophantine equation. How does the control sequence relate to V1? And can we describe, for example, a transient control? So here's the control sequence as a function of V1. What about the control energy as a function of V1? Okay, I realize this last question needed to be changed. How can we control the system when both the control magnitude and the control energy have limits? Okay, so we have a number of things going on all at the same time. How can we handle all of those things? So in terms of performance, we need to look at this matter of figures of merit. So what are figures of merit? Basically, they're a measure of the ineffectiveness of a design. So in particular, rise time, settling time, overshoot, undershoot, steady state error, delay time, subsidence rate. These are some of the issues that are commonly referred to as figures of merit. And so we've talked a little bit about these things, some of these. Again, with our 2 degree of freedom structure, we need to find the controller C1 and C2 to work with this system, where we're now considering our plant in discrete time. And so again, we could have obtained this either through the H transform or through a system identification process. And the solution to our ripple-free deadbeat problem, the basic ripple-free deadbeat problem, involves these 4 polynomials. 3 of them are actually controller polynomials, and then this one is just an additional polynomial that comes out of the derivation of of the controller. So, as I mentioned, these two polynomials are concerned with performance. These two are concerned with robustness. So we're primarily going to be focusing on the use of V1 to work with our problems. Here are the actual signals from U, E, and Y that describe the response of the system, and each of them is a function only of V1, not of V2. Okay, so this shows how the performance comes into play. These are functions of V1, not of V2. So you might ask the question, well, where does V2 come in? That's the robustness, and we'll see that when we look at the robustness issues. But for now, we can see that basically the effect of each of these signals is a polynomial in the unknown V1. Okay, so it has some term, and then it has a polynomial that is a function of V1. Okay, where V1 is a factor. Okay, and so in each of these cases we have that. Notice the thing that multiplies V1 differs. Actually, in these two cases it's identical because of the fact that E and Y are very similar to one another. But this one is clearly different. So the control, the error, and the output. So for the most part, the output and the control are the ones we're going to work with. So notice that the error is what we needed to be a polynomial, and it in fact is a polynomial regardless of what V1 is. And so we're good. So U describes the control signal, Y controls the output. Okay. And so in general, again, the signals U, Y, and E depend only on V1, not V2. So again, V1 affects performance, V2 affects robustness. So for now, we're going to primarily focus on step reference inputs. So for the rest of this lecture, we're going to only look at step inputs or set points, constants. Okay, we'll come back later and look at other types of signals, but for now, let's keep it simple and look only at step inputs. Okay, so when we apply a step input, okay, so notice back over here we had NR and DR. Okay, now that we're going to focus on step inputs, those are known. Those are known quantities. Okay, so in particular, NR is just 1, DR is 1 minus Q, and so these all become finite settling signals, and again they all. So here this looks like it has 1 minus Q in the denominator, but actually the numerator is actually going to cancel with that. So. But the important thing is that these are all finite settling signals. And as a finite settling signal, if you recall from the properties of the Q transform, so we have a transient portion and then we have a steady state portion where the system is settled at alpha, some value. And this is the form of the function when we take the Laplace transform of the entire signal. It comes out to be like this. And so you can see how this looks like that. Okay, and so we're going to use the property of finite settling signals here. So here is our signal U, and I can write it this way. And so I have U1 of Q, which is the transient portion, and then this is the steady state portion. Okay, so it turns out that we can show that U steady state is actually given by the inverse of the DC gain of the system. Okay, and so now U1 is going to take into account V1. Okay, and so U1 takes into account V1, and the degree of V1, it determines this value N1. N1 is the degree of dP plus the degree of V1 plus 1. Okay, so this is actually the transient control signal. Okay, and it is, although it may not be obvious, this is a polynomial. Okay, this is so even though it looks like it's a rational function, so notice that if Q is equal to 1, dP of 1 times 1, this is just a polynomial. This has a root at 1 minus Q. And so this is actually a polynomial even though it doesn't look like it. So this is the transient response, and so in terms of maximum control magnitude, that it usually occurs in this transient response, and so we can describe exactly u1 as a function of v1, and this is just a polynomial. Okay, so that's important. u1 is just a polynomial. Okay, so by way of example, we consider this plant. We go through and compute the Diophantine solutions. So here's n1 min, q1 min, n2 min, dc min. Okay. Notice that the dc and the q1 are always going to be monic polynomials. So you should always expect that. And so, in fact, here we get that. Okay, so this is now our minimum order solution. So let's consider v1 to be a polynomial, first order polynomial. And v1 has two coefficients, v1 0, v1 1. So v1 0 is the coefficient multiplying by the 0 power of q. This is the multiplying the 1 power of q. So that's where the subscripts come from. So here's the transient control sequence. Okay, this is what we have. And we actually plug in the values of NP and DP. So notice that U1 has two parts, U1A and U1B times V1. Okay, so U1A is this part, and when we simplify it down, again, so it boils down to this. This, again, has 1 minus Q as a factor. When we factor it, this is what we get. So this is, but using polynomial division, we can find U1A. And so the transient control sequence is given by this expression. And again, it is a function of V1 0 and V1 1. Okay, and so if we were to gather coefficients in Q, okay, gather coefficients. So this is the coefficient times Q to the 0. This is the coefficient times Q to the 1. I'm not sure why there's a plus there. Okay, I fixed it. All right, so I need to keep up with these little errors, or they just accumulate and it creates a lot of confusion. Anyway, so basically, having collected the coefficients in Q, I have this corresponds to the control sequence. Each of the coefficients in Q corresponds to the value of the control at that time. So this is U at time 0. This is U at time 1. This is U at time 2. This is U at time 3, and so forth. So we actually can, by collecting the coefficients in Q, actually get the control sequence. So we know the control sequence. So now that we know the control sequence, suppose we want the control magnitude to be less than 10. Well, basically that gives us a set of inequalities. Each of the coefficients must be less than or equal to 10. So here are the coefficients written in terms of V10 and V11. And so basically we're going to get a set of 4 inequalities. So here are the inequalities. And each of these inequalities says something. That is, for example, V10 that satisfies this inequality must be in this region between minus 49/5 and 51/5 and so forth. Some of these inequalities have both variables relating. Okay. Now, just looking at these inequalities, it's kind of overwhelming to try to figure out, okay, what values of V10 and V11 will satisfy all 4 of these inequalities. It's not easy. Well, one way to do it, and in this case we can actually do it, is to do it graphically. I can plot these inequalities. So these are the inequalities. These are plots of those inequalities. Each of these bands corresponds to being, greater than this value, less than this value, in between two things. And so here are the actual inequalities. So this red band corresponds to this inequality. This cyan band corresponds to this inequality. This is this inequality, and so forth. The blue is this inequality. So I have all of these inequalities, and now I look at them here. So I've kind of made them a little transparent, and so you can see better how they overlap. And so again, just kind of fading it to background. Here is the region we're looking for the values that will satisfy all the inequalities. And so it's this area that we're looking for, and any value in this area will work. And so in this particular case, notice that 0, 0 is it's a value that's in that region. So in this case, the minimum order solution will actually work in this particular problem. I just happened to find one that was that way. So if I plug in 0, 0, this is how the inequalities play out, and in fact they're all satisfied. So the minimum order solution actually works. So in this case, the control sequence is this, and clearly, in fact, all the values are even less than 1 in this particular case. So this is perhaps not a good example because it was trivially satisfied by the minimum order solution, but at least you see some of the process. Okay, so if we choose now the values 1 and 1, we can see that also works. Okay, that also gives us values that are of magnitude less than 10. Okay, so again, here we've looked at a specific example. Let's move on to generalize this to the general case. And so in order to generalize it, we're going to need tools to work with that will allow us to look at it in the general case. Now, the main reason we use these guys is because these things allow us to transform polynomial problems into matrix problems. So here's an important property for vectorized polynomials. So suppose I have two polynomials, f and g. So that corresponds to these two polynomials. So notice that these are different order. Okay, so two different polynomials. And so the vectorized form of the product of f and g. Okay, so that's the vectorized form. So here we have f and g vectorized. We can write this as the expanded matrix of f expanded n2 plus 1 times vectorized g. So notice that g, even though it's degree n2, it actually has n2 plus 1 coefficients. So in order to multiply with the expanded matrix, we need to expand that. We need to add n2 plus 1 columns. So again, the stair-step kind of thing. So this product is equal to this product. That is, I can expand g and then multiply by the vectorized form of f. Okay, so here is the polynomial. So this now is a matrix that includes the coefficients of g times the coefficients of f stacked in a vector. This is the matrix of f multiplying by g coefficients stacked in a vector. So this is an important property in being able to write a polynomial product as a matrix product. Okay, so if you recall, a product in the Q domain is actually a convolution in the time domain. So this is actually performing that convolution. Okay. So in our problem now, we have a situation like this. Okay. We have u1 of q is equal to some polynomial, u1a of q, minus something else that involves our unknown v1. Okay. So we can vectorize this polynomial this way. So the vectorization of this is equal to the vectorization of this minus the vectorization of this quantity. Notice I have a product here. And so I can do it this way. And notice that dp is given by this. And notice that I need to expand it 2 times. Actually, 2 times because v1 has 2 coefficients in it. Okay, v1 has 2 coefficients, and so this is what we get when we expand all of this. Okay, this is what we get, and so this is this vectorized. Notice that I don't have a q term here, so that's why I get a 0. And then this, notice I have it like this, and then it's shifted over and down 1. So this is the expanded matrix of that. So I can write down now u1 of q, remember, is the transient control sequence. And in this case, I know exactly how to write the values of u0 through u3 and in a matrix form. Okay, so we'll come back later and see what we can do with these things. But for now, we have a way of writing the transient control sequence as a matrix involving the coefficients of our unknowns. Okay, so we're going to set ourselves up for a least squares problem here in just a little bit. But for now, we have it written as a linear algebra thing. I have a column minus a matrix times a column. So all of this is the transient control sequence for this example problem I've been working with. Now, what about the transient output signal? So again, our output signal over all time can be written as the transient versus the steady state. Okay, so in this case, y1 is given by this expression, and y1 is a function of two terms, y1a and then this thing that involves v1. y1a is given by this expression, which incidentally is a polynomial. It may not look like a polynomial, but remember, if q is equal to 1, then this just becomes np of 1, this becomes 1, and the two subtract, leaving 0, which means 1 minus q is a factor of this polynomial in the numerator. Okay, so y1 of q can be written as y1a of q plus, or rather, minus np of q, v1 of q, which can be vectorized this way. Okay, so we have the expanded matrix times the vectorized form. And so those two important signals, the transient output sequence and the transient control sequence, we can now describe in terms of matrices. And so we have some a nice framework from which to work. Okay, so now when it comes to doing things like figure of merit design, we want to design a controller to satisfy certain criteria. So we talked about the performance program already. So how do we go about doing that? And here are the common design constraints: settling time less than some value, overshoot less than some percentage, maximum control magnitude less than some number. So the question is, how would we choose our unknowns to satisfy these types of inequalities? Okay. Well, first of all, in terms of the settling time constraint. Now we're going to look at the settling time constraint. Well, first of all, we know the system is finite settling, and the settling time is less than or equal to the sampling period times the degree of E, which I'm going to call N1. Okay, that degree is actually equal to the degree of NP plus the degree of V1. Okay, so obviously it's affected by the degree of V1. So the larger V1, the longer it takes to settle. And so to have a particular settling time, we need to satisfy this condition. The degree of V1 must be less than or equal to whatever settling time we're wanting divided by our sampling period minus the degree of NP. Okay, so this side, or actually this inequality, doesn't depend upon the actual coefficients or the values of V1. It doesn't depend upon the coefficients of 1. It only depends upon the degree. Now, notice this condition also says something about the sampling period. The sampling period could also be varied. Okay, smaller sampling period, we're going to have a larger quantity here. So anyway, we have this kind of situation. Now, one of the things that this equation tells us is we can't have a negative degree. Okay, so that is, we can't have a negative degree of V1. So we need to have this condition. The sampling period must be less than or equal to the desired settling time divided by the degree of NP. Okay, so this is a requirement if we're going to meet this settling time. Okay, and in fact, we need to have strictly less than if we're going to have any meaningful V1 available for us. Okay, so here I'm going to call the degree of V1 equal to M, and so we're going to assume it satisfies this condition. So if this condition is satisfied, we will settle within the value TS, whatever value that happens to be. Okay, so we have a nice way of looking at it. And again, this is based on the fact that we have a finite settling our system is finite settling. So it's going to settle in a fixed number of steps, and so we just have to determine that number of steps needs to be less than the settling time. Right? So, okay, so that's the settling time. What about, incidentally, the settling time is usually a very difficult one to satisfy for a lot of control problems. So the fact that we can so easily characterize it is really cool. All right, now the overshoot constraint basically requires that m of t be less than or equal to 1 plus the overshoot for all t. Okay, so if we think of the overshoot, 1 plus mp, the output of our system must be less than that for all time. Okay, so that's equivalent to the values of y being less than or equal to 1 plus mp, and here's just a vector of 1s. So when we say inequality here, this column being less than or equal to this column, basically we're saying element by element, each element in this column is less than or equal to each element in this column. And so I'm going to use this guy a lot, a vector of all 1s. And so I call that 1 vectorized, okay? And so we obviously, we need to determine its length, but it's just a vector of all 1s. And then this is y1, the transient response, okay? That's the transient response. So remember, it's going to settle exactly to 1, so we only are concerned with the transient values of y. Okay, so now recall that when we vectorize y1, we get y1a vectorized and y1b, okay? And so that inequality that we just showed basically is equivalent to this inequality. That is, my unknown can be written in terms of my known. All of these are known, okay? And in terms of, in optimization terms, this is called a hard constraint. In other words, v1, so this column needs to be less than or equal to, this is just a column, needs to be less than or equal to this column. Every element needs to satisfy that. Okay. Now, so this is the overshoot constraint. So we've already looked at the settling time constraint. That actually puts that is not affected by the values or the coefficients of v1, only by the degree of v1. So that sets the degree of v1. Okay. And now this actually is a condition on the values or the coefficients of v1. Okay. So that's the overshoot constraint. What about the control magnitude constraint? So if we want the elements of the transient control sequence to be less than some value, this is equivalent to actually to these two inequalities. That is, u of kt must be less than or equal to um, and minus u of kt is less than or equal to um. Okay, and so since the transient control sequence is written in vectorized form this way, then this inequality actually gives this first row, this inequality, that gives that first row, and then this inequality actually gives that second row. And so we can now describe the control magnitude constraint in terms of vector inequalities. So between the two, I can now combine constraints. So that is, I can combine the overshoot constraint and the control magnitude constraint this way, put it all into a single inequality. Now, I've written them in a particular form. I have something times our unknowns less than or equal to some column. This is actually a column, okay? And so why do we want the constraints in this form? Well, it turns out that later on, we're gonna show you a really awesome tool, and that awesome tool wants the inequalities in this form. Okay, so that's why we put them in that form. All right, so we have a bunch of inequalities. Now, when we looked at in the previous example, when we looked at the set of inequalities, we saw these bands, you know, and the overlapping of the bands gave us the region of our coefficients that we could work with. Well, in general, we won't be able to just plot those bands and see the overlap and discern where the coefficients of v1 need to be. So it's helpful to have computational tools that can help us solve that problem. And so we're really headed towards using some some serious computational tool. Okay, so for now, here, given this transfer function, I get this in the discrete time. And I have the constraints. I want overshoot less than 10%, control magnitude less than or equal to 1.5. So I go through and I form my U1 of A, which is given by this expression. Okay, and so here I have this expression, U1 of A. U1B is given by this expression. So it's this expanded 2 times. Okay. Similarly, I can go through and find my Y1A and my Y1B, and I showed the formula for how to obtain those. And so here are the matrices for that particular problem. Okay, and so the overshoot criterion. So this criteria, the criterion for the overshoot, using these matrices, basically leads to these inequalities. Now here I'm only looking at the overshoot. So this does not take into account the control magnitude constraint. This is just the overshoot criterion. Okay, and so V1 has, in this case, again, just 2 coefficients. I'm looking at it in the 2 coefficients case because then you can kind of see what's going on. But basically, for every coefficient here, you can think of it adding another dimension in the space of parameters. So in this case, we have 2 unknowns. That gives us a 2-dimensional parameter space, okay, which is a plane. Right? If we had a third coefficient, so if we had plus V12 Q squared, that would give us a 3rd dimension to look at. And again, it starts getting really complicated then. And basically, each row in this set of inequalities basically gives a line that divides the entire space in half. Okay, so the inequality says I'm on one side of this line. Okay, and I have another line over here, and I'm on this side of that line, and so forth. So each of these inequalities gives us a line, and it basically divides the space in half. Okay, so this divides it over here, this divides it over here, this divides it over here, so forth. And so so those set of inequalities actually, when I plot them and overlap them, I get something that looks like this. Okay, so I use different colors to overlap them. And I can see there's a region in here where all of those inequalities are satisfied. And notice the origin is not in that region. Okay, it's not in that region. So that's the control, that's the overshoot constraints. The control magnitude constraints basically come out to be this. And you can see, even for this simple problem, I'm getting a lot of constraints. It's getting really complicated. So clearly, I'm not going to be wanting to do this in general. I'm only showing you kind of what's going on in this 2-dimensional case to kind of give you a sense of what's going on. But really, you're not going to be expected to do plotting these inequalities like this, because it's, first of all, it only works for something that has 2 unknowns. Second of all, in general, we may have lots of inequalities. Okay, so this is going to be way too complicated. But I just kind of want to give you the sense, the feel for what's going on behind these inequalities. So these inequalities, and again, for the control magnitude constraint, we get these bands, right? And so these show the different bands associated with the different inequalities. And again, where they overlap is where they're all in common. So in this case, we get the region in here that satisfies all the inequalities. In this case, this point is in this region. Okay, so notice it's some kind of weird polynomial, polygon. Okay, and so that's what we have. And so it turns out this solution for V10, V11 satisfies all the constraints. We can actually go through and show that it satisfies all the constraints. Okay, if we go ahead now and we actually simulate the system with this controller and we look at the response, here's our response. Okay, and so notice we do have some overshoot, but it is less than 10%. Our control magnitude is less than or equal to, it's actually strictly less than 1.5. So we're good. Success. Yes, the sweet smell of success. Okay, so this is the this is how all of this this works. So we were able to in this case to develop a controller that gave us the desired control magnitude and the desired overshoot. Okay, so notice we still had some overshoot, but at least it wasn't like that huge overshoot like we had before. So here's the SIMULINK model that we use to do this simulation, and a number of ways of doing this. So here, for example, I use an FIR block to implement the N1 and N2 numerator and denominator, and then I used 1 over the denominator to simulate this transfer function. Okay, so this is the controller that we would use. This is the form that we would use. So in our case, here I actually have it as a function of Q. The actual SIMULINK blocks you would use would basically have it in terms of Z inverses. So you would use the form that involves Z inverse. And so I've put this all into the subsystem and put this into this block diagram so it looks like the block diagram we had at the beginning. So this we now have an important tool for being able to handle performance issues. Okay, now we're not done yet with this performance issue. We've done that. We've set everything up to do performance. We've looked at settling time, overshoot, control magnitude. Those 3 figures of merit, and we figured out how to put them into matrix form. Now, when we come back next time in our next lecture, we're going to be looking at a very powerful tool for solving those kinds of problems. Thanks for watching.